All right, it's 2 p.m. So if you are on Zoom, please type here in the chat so that I can take the roll. Today we're going to be talking about several different concepts that are commonly known as our circuital laws. The first one that we are going to talk about is Ohm's law. So way back in the early 1800s, a German physicist by the name of George Simon Ohm did a bunch of experiments. And I will briefly recap the experiments that he did here. So he took a material under test, call this MUT for material under test. And what he did is he applied a voltage across the material. Let's call this V test. And what he did was he measured the voltage drop across the material, and he measured the amount of current flowing into the material. And he found that there is a linear relationship between these two quantities, which he called resistance, where the resistance of the material under test, R, is given by the voltage drop over the material divided by the current flowing through the material. Resistance R has units of ohms, where 1 ohm is equal to 1 volt per 1 amp. Resistance as a property can be defined as a measure of how easily current passes through a conductor. And this property is likely what many of your first experience with resistances was. As part of the Engineering 120 class, on your first or second day of classes, you were asked essentially to design a small circuit that would cause a light-emitting diode to blink. So you had something like this, where you had a 5-volt source that was being supplied by the digital output pin of your Arduino microcontroller. Then you had a resistor here. If my memory serves me correctly, you were asked to use a 222 ohm resistor. And then you had your light emitting diode, like so. And the purpose of the resistor in this case was to limit the amount of current that was flowing through the LED, because without it, you would quickly burn the LED out. It would shine very brightly for a number of seconds, and then it would be irreparably damaged. With the resistor in place, limiting the amount of current that can flow through the LED, the LED could shine for hours, days, etc., without actually suffering any damage. Okay? So resistors are used largely to limit current. And they do this by converting electrical energy into heat. So the coil for an electric stove, right? Something that looks kind of like this, if you allow me to draw a crappy picture. You have an electrode coming in. And then this guy right here jumps over the rest of the coils. So on an electric stove, you have a heating element or something like that. That's simply just a resistor. You pass a current through it. The material that the coil is made of resists that current flow and causes the coil to heat up, thereby boiling your water or heating up your pan or whatever it is that you're trying to do. And from this example, we can actually observe an alternative way to express resistance, okay? R, resistance, is dependent on the material of interest due to its resistivity, which is represented by rho E. And then it's also dependent on the geometry of the property by length divided by cross-sectional area, which is why a heating element like a coil is such a good way to create a heating element resistor. It has a very, very long length and a very, very small cross-sectional area, which means you can get a lot of resistance out of it and therefore convert a lot of electrical energy into heat. Before we move along from this, I want to talk about a couple of different circuit terminology things that you may have heard of and how they relate to resistance. So the first thing that I want to talk about is what's called a short circuit. So a short circuit is typically thought of as a bad thing when you hear about it in an electrical device, okay? Typically what it means is that there is an unwanted electrical connection that is causing some sort of electric signal to bypass its intended path, and the device that you're trying to use doesn't operate in the way that you want it to. We represent short circuits on a circuit diagram literally by just a wire. Okay. And we treat a short circuit as an element or a wire that has a resistance of exactly 0 ohms, which means from Ohm's law that the voltage drop across a short circuit has to be exactly 0 volts. An open circuit we represent that on a schematic diagram as really kind of the absence of a wire, right? It will have an infinitely large resistance, and in an open circuit, since there is not a closed path, the current that flows through the open circuit has to be 0 amps. Okay. Now, a generic resistor, as I've shown you a minute ago, has a schematic symbol that looks like a squiggly line like so. And the resistance is represented by some finite value. Resistors obey the passive sign convention, which means if we have a voltage drop across our resistor VR like so, and a current that's flowing into the positive polarity terminal IR like so, then our resistor is absorbing power. One interesting thing about resistors is that they can actually never supply power because they don't have any means by which to store electrical energy. As I mentioned previously, all they can do is convert electrical energy into heat. Therefore, they must constantly be absorbing power while they convert the energy into heat. They can never store it. And so the power that is absorbed by a resistor has to always be a positive quantity. if we look back here at our original expression, George Simon Ohm decided that the ratio of voltage and current, expressed as we have here, would be called resistance. Well, we can actually express the ratio of voltage and current in a slightly different way, which we will call conductance. Okay. So conductance is G, and it is simply the reciprocal of resistance, or the ratio of current to voltage through a particular medium. Okay. Conductance, the units of conductance are the Siemens, where 1 Siemen is equal to 1 ampere per 1 volt. And conductance is defined as a measure of how easily current passes through. So it's literally just the opposite of resistance. Now, I have a bachelor's degree in electrical engineering, a master's degree in electrical engineering, and a PhD in engineering with a concentration on micro and nanoscale electronics. The reason why I am mentioning this is because I can tell you rather definitively that for the overwhelming majority of applications, conductance isn't a particularly important quantity, okay? It will show up when you're analyzing problems using network theory, and it will show up when you are developing relationships regarding transmission line theory. Other than that, conductance really doesn't play a big role in circuit analysis. So I would behoove all of you to acknowledge that conductance exists by simply taking the reciprocal of conductance and then treating it as a resistor and moving on about your business. That will be much, much easier on you all than having to learn and develop rules for conductances that are opposite of what we are going to develop for resistors, okay? So we can develop a couple of equations here, particularly power relationships for both conductors or conductances and resistances using some of the information that we've already developed in this class. So for example, we know from our last class meeting that power P is equal to the product of current I and voltage V. Let me make this P as a function of time, right? Well, using Ohm's law, we could express I as V over R, giving us the power absorbed by a resistor is the square of the voltage drop across the resistor divided by the resistor value, or in terms of conductance, this would be the square of the current multiplied by our conductance G. We can also use Ohm's law to express the voltage as the product of current and resistance, giving us the relationship I squared times R, or using conductance, V squared times G. So hopefully the overwhelming majority of this little section here was reviewed, right? Before we move along to Kirchhoff's current law and Kirchhoff's voltage law, does anyone have any questions regarding Ohm's law? All right. So let's talk about Kirchhoff's voltage law first. So Kirchhoff's voltage law states that the sum of the voltage drops around any closed path must be zero. What Kirchhoff's voltage law really is here is the law of conservation of energy for circuits. Because as we learned in our last class, a voltage drop is related to a transfer of energy. And so Kirchhoff's voltage law effectively states that the total amount of energy transferred in a system has to be equal to zero, meaning that energy in a system cannot be created or destroyed. Okay? So we can put Kirchhoff's voltage law into practice to determine unknown voltages in a circuit. So let's say that we have the following circuit where we have a 10-volt source like so. And then some element A over which we have measured a 5-volt drop, having this polarity, positive polarity on the left. And then we have some element B where we are going to determine what the voltage drop over element B is with the positive polarity on the right. And then we also have a 3-volt source like so, positive polarity on bottom. Okay. So Kirchhoff's voltage law tells us the sum of the voltage drops around this closed path has to be equal to zero, which will allow us to determine the unknown voltage VB. So what I like to do when applying Kirchhoff's voltage law is I like to imagine a current. And I choose a direction for this current, typically leaving the positive polarity terminal of the largest source. Okay, I'm just going to call this current I. And what I do is I follow the current around its clockwise path. Okay. So if I were to write a Kirchhoff's voltage law expression for this particular circuit, I typically start in the bottom left-hand corner, and then I follow the current around. Since the current I is flowing into the negative polarity terminal of the 10-volt source, I would write this as negative 10 volts. Then it flows into the positive polarity terminal of the 5-volt drop across element A, so that's plus 5 volts. Then we see the negative polarity terminal of the voltage drop VB, so that's minus VB. And then we see the negative polarity terminal of the 3-volt source, so that's minus 3 volts. And we're now back at the node that we started from. So we're finished by setting this equal to 0. And then we can solve for that unknown voltage VB. So using what I hope is a trivial amount of algebra, we have VB is equal to negative 10 volts plus 5 volts minus 3 volts. is equal to -8 volts. Does anyone have any questions regarding that analysis? All right. So one thing that I have seen students struggle with is determining a voltage like this that I'm about to show you. So what if we wanted to know this voltage drop, Vx? So one thing that students seem to find difficulty with is acknowledging that there can be effectively a voltage drop across this open circuit in the middle of this circuit. So imagine that Vx is simply the voltage drop that you would measure by applying a multimeter connected at this point in the circuit for the positive. So let me do it in red, because that's the color of the positive polarity terminal on most multimeters. And this point in the circuit down here, which would be the negative polarity terminal for most multimeters. How could we go about writing a KVL expression to solve for this voltage? Well, even though there isn't a current that's going to flow down through that open circuit, we can still apply Kirchhoff's voltage law in pretty much the exact same way, okay? So our second application of KVL here to determine this voltage Vx will be very similar. We see the negative polarity terminal of our 10-volt source first. Then we see the positive polarity terminal of our 5-volt source. And then we see the positive polarity terminal of our voltage Vx, and we have returned to our original node of interest. We can solve this then very easily and see that Vx is equal to 10 volts minus 5 volts, which is 5 volts. Now, the problem that a lot of people have with this is that, again, there's no current flowing down through the path where that voltage Vx appears. But that's actually absolutely okay, because Kirchhoff's voltage law is simply adding up voltages. Current is not required, okay? KVL says the sum of the voltages has to be equal to 0. Does not matter what the value of the current actually is. We can use Kirchhoff's voltage law in combination with Ohm's law in order to do a little bit more robust circuit analysis, okay? So let's say that we have the following circuit. Where we have a 120 volt source, a 30 ohm resistor, and then we're going to have a dependent source that provides a voltage of 2 Vx, where Vx will be the voltage drop across this resistor on the right, having this polarity, and this resistor will be a 15 ohm resistor. So again, I'm going to choose arbitrarily to say that there is a current I that's flowing around this circuit. And I always choose I to be leaving the positive polarity terminal of the largest voltage source, okay? So if I write the KVL equation for this circuit, what I have is negative 120 volts And then I see the 30 ohm resistor, okay? Now, I don't know what the polarity of the voltage drop across the 30 ohm resistor is. I can't simply ignore it, so I just have to assume it. So I would like for one of you all to tell me whether you believe the voltage drop over the 30 ohm resistor, which I'm going to call V30, is positive polarity terminal on the left or positive polarity terminal on the right. You cannot get this wrong. Literally just choose left or right.
Right.
Right, okay. So we see the negative polarity terminal first. So we're going to have minus V30. We have the positive polarity terminal of the dependent source. So this is going to look like twice Vx. And then we have the negative polarity terminal of the voltage source. So we have of the voltage Vx. So we have minus Vx. We set this equal to 0. And we can do a little bit of algebraic manipulation here and say that negative V30 plus Vx is equal to 120 volts. Is everybody okay with that algebraic manipulation? So we have a little bit of a problem here, in as much as we have a single equation, but two unknowns. This is where Ohm's law is going to come into effect, okay? So we're going to write two Ohm's law equations. The first thing that we're going to do is write an equation for V30. So we are going to express our voltage drop V30 in terms of that current I. Okay. So using Ohm's law, where V is equal to I times R, we are simply going to have I times 30 ohms. But there is an important thing that we need to notice here. Our current I is flowing into the negative polarity terminal. Whenever our current is flowing into the negative polarity terminal of our resistor, we need to include a negative sign in our Ohm's law equation. What this does is forces this resistor to absorb power. Okay? Similarly, we can write an Ohm's law expression for Vx, where we are going to have our current I, which flows into our 15 ohm resistor. The current is again flowing into the negative polarity terminal, so we need to include this negative sign here. And now we can substitute these two Ohm's law equations into our Kirchhoff's voltage law equation, and we will have a single equation with a single unknown, the current I. We can solve for that and then be able to determine our voltage Vx. So we have negative V30. So this is negative times negative I times 30 ohms plus Vx. So this is minus I times 15 ohms is equal to 120 volts. So we have 30 ohms times I minus 15 ohms times I, leaving us with positive 15 ohms times I is equal to 120 volts. And from this, I is equal to 120 volts over 15 ohms. That's the 8 amperes. Using this result, Vx is negative 8 amperes times 15 ohms is equal to negative 120 volts. What if we wanted to know the power supplied by our dependent source? How can we determine that? So when we want the supplied power, we need the voltage drop across our element of interest and the current flowing into the negative polarity terminal, okay? So for our dependent source, the voltage drop across our element of interest is simply twice Vx, because that's what we're told, right? This voltage source supplies 2 Vx of voltage. The current that's flowing into the negative polarity terminal is negative I. And we could then simply substitute in our numbers, right? So this would look like negative 2 times Vx of negative 120 volts times I, which is 8 amps, tells us that our dependent source is supplying positive 1,920 watts of power. All right, one last thing that we can use Kirchhoff's voltage law for here really quick is to make an observation. Okay. So let's say that I have the following circuit. Where I have 15 volt source in parallel with a 12 ohm resistor, and I also have in parallel a 5 ohm resistor. Okay. And I want to know the voltage drop over the 12 ohm resistor and the voltage drop over the 5 ohm resistor, which I'll call V5. Okay. So if we apply Kirchhoff's voltage law around this loop, what we'll find is that negative 15 volts plus V12 is equal to 0, which means V12 has to be equal to 15 volts. Similarly, I could apply Kirchhoff's voltage law around this loop, and I would get negative 15 volts plus V5 is equal to 0, implying that V5 is equal to 15 volts. So effectively, whenever I have elements that are in parallel, Kirchhoff's voltage law forces all of these elements to share the same voltage, okay? So all elements that are connected in parallel will have the same voltage drop over them. So this is an alternative way for us to view whether or not things are connected in parallel. If they have the same voltage drop, they are in parallel. They're behaving as if they're in parallel at the very least. All right, now let's talk about Kirchhoff's current law. There are actually three different ways that we can formulate Kirchhoff's current law. And they all mean effectively the exact same thing. So what I'm going to do here is I'm going to draw a simple picture. Having several wires leading into a node, and each of these wires will be carrying a current. So let's say that we have a current I1 flowing through this branch, a current I2 flowing through this branch, a current I3 flowing through this branch, a current I4 flowing through this branch, and a current I5 flowing through this branch. Formulation number 1 states sum of the currents flowing into a node must equal the sum of the currents flowing out of this node. So our Kcl expression using this formulation would look something like this. Since I1 is flowing in, it'll be on the left-hand side of the equal sign. I2 is flowing out, so I'm going to place it on the right-hand side of the equal sign. I3 is also flowing out, so I need to add it to I2. I4 is flowing in, so I need to add it to I1. And finally, I5 is flowing out, so I need to add it to I2 plus I3. So we have the currents flowing in equal to the current flowing out. That's our first representation of Kirchhoff's current law. Our second representation is the sum of all currents entering a node must equal to 0. This is not saying that I1 plus I4 is equal to 0. Instead, what it means is that we can treat I1 as flowing in, so that's a positive current. Since I2 is flowing out, a current of negative I2 is flowing in, so we have minus I2. A current of negative I3 is entering the node, so minus I3. A current of positive I4 is entering the node, so we have plus I4. And the current of negative I5 is entering the node, so we have minus I5. And we set this equal to 0. It's literally the exact same expression as we got for formulation number 1, except that we moved everything from the right-hand side of the equal sign over to the left-hand side. Our third expression, or our third formulation, is that the sum of all currents exiting a node must equal to 0. So in this case, negative I1 is exiting, positive I2 is exiting, positive I3 is exiting, negative I4 is exiting, and positive I5 is exiting. And so that's what our equation will look like. And it's literally the exact same thing as we got in formulation number 2, except multiplied everything by a factor of -1. So all three of these representations of Kirchhoff's current law literally give us the same results. It just depends on what perspective we have as to which formulation that we will use. I believe that most of you are currently familiar with formulation 1 more so than the other 2 formulations. And I do tend to use formulation number 1 at times. But the one that I typically default to is actually this guy over here, number 3. And when we cover nodal analysis in roughly a week's time, the reason for this will become obvious. But in short, if we use this particular formulation using that particular analysis tool, we wind up getting the least amount of negative signs. And I know that I make a lot of algebraic mistakes when there are too many negative signs. So for you guys, I would prefer that you simply just choose whatever you're comfortable with, okay? So let's work an example problem. Let's say that we have the following circuit where we have an 8 amp source connected in parallel to some element A, which we have determined carries a current of 1 amp. We have a 2 amp current source, and we have some element B over here, and we want to know the current carried by element B, I sub B, in the up direction. So one of you, please choose which formulation of Kirchhoff's current law we are going to use, number 1, number 2, or number 3.
Let's see number 3.
Number 3, okay. Now, if you don't mind, also choose whether we are going to apply formulation number 3 at the top node or the bottom node.
Top.
Top, okay. So I'm just going to write this down, KCl, top, number 3. So for formulation number 3, we are summing the currents that are exiting our top node. So what I like to do in a situation like this is I like to indicate things here real quick. So this current flowing down is going to be a positive quantity. This current flowing down is a positive quantity. This current flowing down is a positive quantity. And this current flowing down is a positive quantity. And I'm simply adding all of those together. And what I'm going to do is I'm going to relate those branch currents that were indicated on the original circuit to these currents that I've outlined in orange and write my Kcl equation, okay? So the 8 amp current is in the opposite direction as my orange arrow. So that means it's going to be negative 8 amps. The current flowing down through element A is in the same direction as that 1 amp that I've indicated. So I will have plus 1 amps. The current flowing down through my rightmost source is in the same direction as the 2 amp source. So I will have plus 2 amps. And then the current flowing down through element B is in the opposite direction of what I've indicated for IB. So I will have minus IB and set it equal to 0 and do a little bit of algebra. and I will find that IB is equal to -8 amps plus 1 amp plus 2 amps is equal to -5 amps. Much like what we observed with Kirchhoff's voltage law, we can also use Kirchhoff's current law and Ohm's law in combination to perform a little bit more of a complex analysis. Okay, so let's say that we have the following circuit. Where we have a 5 amp source, a 10 ohm resistor, a 1 amp source, a second 10 ohm resistor, and a 6 amp source. Direction up. And our goal here is to determine this voltage V. Now notice this voltage V is actually common to all of these components because all of these components are connected in parallel. So this will actually be the voltage drop over every element in this circuit. Okay? So we're going to start things off by applying Kirchhoff's current law, KCL. And in this instance, I'm going to use formulation number 1 and bottom just to be different than the last time. Okay, just to show people who are interested how we might go about doing that. Okay, so currents that are leaving the bottom node have to equal currents that are entering the bottom node. And just for the sake of argument as well, because I'm going to be applying Kirchhoff's current law, I need to identify the currents flowing through my resistors. So I'm going to call this current right here I sub L, because it's for the 10 ohm resistor on the left, and I'm arbitrarily choosing that one to be down. And I'm going to call this current right here I sub R for the current flowing through the 10 ohm resistor on the right, and I'm arbitrarily choosing this one to be up. Okay, so if I apply Kirchhoff's current law, formulation number 1 at my bottom node, I have 5 amps of current that's leaving. I have a current of IL that's entering. I have a current of 1 amp that's leaving. I have a current of IR that's entering, and I have a current of 6 amps that's leaving. And so if I do a little bit of algebraic manipulation here, what I will find is that I will have IR minus IL is equal to 7 amps minus 5 amps I made a mistake. The 5 amps was leaving, so it should have been on this side of the equal sign. Does everybody understand that? So we're considering the currents leaving on the left-hand side of the equal sign, the currents entering on the right-hand side of the equal sign. Since the 6 amp current is leaving the bottom node, it should have been on the left-hand side of the equal sign. So So I'm going to redo this a little bit just to get rid of negative signs because again, I tend to make mistakes. So on the left-hand side, I'm going to have 5 amps plus 6 amps minus 1 amps. So that's going to look like 10 amps. And on the right-hand side of the equal sign, I'm going to have IL minus IR. There we go. Again, we have one equation and 2 unknowns. So we're going to need to use Ohm's law to relate our current IL and IR to that common voltage. So IL will be the voltage drop V divided by the 10 ohms of resistance. Well, the current IL is flowing into the positive polarity terminal. So my Ohm's law equation should have a positive sign. For my current IR, I'm again going to have V over 10 ohms, but my current IR is flowing into the negative polarity terminal of the voltage. So I should include a negative sign right here, and I'll simply substitute that in. So that I'll have 10 amps is equal to V over 10 ohms minus negative V over 10 ohms, which looks like 10 is equal to twice V over 10 ohms. And from this, V is equal to 10 ohms times 10 amps over 2, or 50 volts. All right. So let's look at one other quick example before we move along. In this case, we're going to have a circuit in which all of the elements are connected in series and observe something. Okay. So let's say that we have a 5 amp source, three ohm resistor, an 8 ohm resistor, and a 4 ohm resistor. I'm going to denote my nodes like this because I just want to look at something here real quick. So the current flowing into this red node on the upper left is obviously 5 amps. And since there's no place for the current to branch off, the current exiting here has to also be 5 amps. That same 5 amps of current has to flow into this blue node and out of the blue node, into the orange node and out of the orange node, and then into the teal node and out of the teal node. And so from this, we can say that all of the elements that are carrying 5 amps are all connected in series. Okay? So that's another way for us to determine when elements are connected in series, is when they're carrying the same amount of current. All right, I have one last problem that I would like to work with you guys today. And it is, I would argue, a pretty significant step up in difficulty. Okay. In this particular problem, we are going to have to use a combination of Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law to solve for our quantities of interest. So the circuit that we are going to analyze is this guy, where we have a 60-volt source connected to a 20-ohm resistor connected to this dependent voltage source, and this is going to be a current controlled voltage source, which I believe is the first time we've seen one of those. And we're going to have this connected to a voltage controlled current source, where this will be 1/4 of Vx. And then over here, we will have a 5-ohm resistor. Okay. Let's call the voltage drop across our 20-ohm resistor Vx, and let's call the current through our 20-ohm resistor Iy. And our ultimate goal here will be to determine the power supplied by our current controlled voltage source and the power supplied by our voltage controlled current source. So let's also figure out the power supplied by our 60-volt voltage source. So in order to determine these things, we are going to need to solve for the quantities of Vx and Iy. Can anybody help me out with either of those things? Anybody have any thoughts? All right, so since this circuit is a little complex, one thing that I'm going to do is I'm going to identify my nodes. So
Dr. Hartman, I have a question if you don't mind.
Absolutely, please.
So when solving equations that involve like KVL and KCl, would identifying nodes always be your first step? Like, I'm just confused about like how you would approach problems like this, especially as they get more difficult, like in the web works.
So for this particular problem, based on our current amount of circuits knowledge, we're really just gonna kind of throw the kitchen sink at it and see what sticks, okay? Later on in this class, we will develop more strategic algorithms by which to analyze circuits, but we're not quite at that level of understanding that's needed to really figure out what's going on with them. Identifying nodes and things like that is really kind of always a good first step until you get very comfortable with the more advanced circuit analysis techniques that allow us to, kind of charge through a difficult problem with a particular process in mind. Okay. Was that remotely helpful?
Yes, sir.
So I've got a node on the top left. I've got a node on the top right. And then I've got a node on bottom. Can we all agree with that? Let's start there. So I'm going to take your silence as agreement so that we can move along. So we've identified our nodes and I have made two observations. My first observation is that the 60 volt source and the 20 ohm resistor are connected in parallel because they share the red node and they share the green node. My second observation is that the dependent current source and the 5 ohm resistor are in parallel because they share the blue node and they share the green node. Are either of these observations helpful? Let's start there.
Yes.
Yes. Do you know which of the two observations is helpful? So what did I say earlier about things that are connected in parallel? When elements are connected in parallel, they share the same voltage, okay? So that means the 60 volt source and the 20 ohm resistor have the same voltage, which means Vx has to be, 60 volts. It cannot have a different voltage because these two elements are connected in parallel. Are we okay with that?
Yes.
All right. So since I know the voltage drop over my 20 ohm resistor, I would argue that I can figure out what IY is now just using Ohm's law. So IY would be Vx divided by 20 ohms. Substituting in my value for Vx, this is going to look like 60 volts over 20 ohms or 3 amps. So what I'm going to do is I'm going to indicate this current of 3 amps on my schematic diagram. Okay. Now, since I know that IY is 3 amps, this 5 IY dependent source is now a known quantity, right? 5 times 3 is 15 volts. And similarly, since I know Vx, this is no longer behaving like a dependent source. So Vx, or 60 volts over 4, 60 over 4 is 15 amps. So this is a 15 amp source. So now we've got rid of all of our dependencies. So things should look a little bit more manageable. okay? So we have actually gleaned a whole heck of a lot of information from this circuit simply by observing that the voltage source was in parallel with an element, which allowed us to know what the voltage drop over that element was. And then simply using Ohm's law to find out what that current through that element was, and then plugging these dependencies in. So where can we go from here? Well, let's talk about what pieces of information we need, okay? I'm going to clean things up just a smidge here so that it's not quite busy looking. Since we are asked to find the power supplied by our current controlled voltage source, what we need to determine is current flowing into the negative polarity terminal. So I'm going to call this ICC VS because we already know the voltage drop across it. Okay. Similarly, because we're trying to find the power supplied by our voltage controlled current source, we need to find the voltage drop across that current source. And I want the current to be flowing into the negative polarity terminal so that the product of current and voltage gives me the supplied power. So I'm going to call this voltage VC CS. And lastly, I need to determine the power supplied by our 60 volt source, which means I need to know the current that's flowing into the negative polarity terminal of our 60 volt source, which I'm going to call I 60 volts. So our next steps will involve figuring out how to determine those three quantities. Does anybody have any thoughts?
Well, we already have like 3 amps below the 20 ohm resistor, and we know that there's 15 amps leaving the VVCCS
Right.
part. Would there be any way to find out what current is flowing through the 5 ohm resistor?
So that's a very good intuitive step there, okay? You've made a very, very good observation. The only thing we don't know in order to determine the current I 60 volts is the current flowing through the 5 ohm resistor. So let's go ahead and throw a label on that guy real quick as well. I'm just going to call this I 5 ohms. Now, to determine the current flowing through that 5 ohm resistor would require us to know the voltage drop across that 5 ohm resistor, which would enable us to apply Ohm's law. Since the voltage controlled current source and the 5 ohm resistor are in parallel, I would argue that this voltage here is also VVC CS. So once we can figure out what the voltage drop is across the current controlled current source, we're only one step away from figuring out what that I 5 ohms is. So that's a very, very good observation that you made, but it still relies on something else that we have yet to figure out. Anyone else have a thought? All right, I'm going to give you a hint, okay? As we just discussed, this voltage VVCCS is a pretty important thing because that will effectively allow us to calculate two of the three powers that we're looking for. So one way that we could go about solving for that particular voltage is by applying Kirchhoff's voltage law around this loop. So we're going to start from this bottom left-hand corner, go across like so, go down like so, and come back across. So this is where we're going to write our KVL loop. The reason I chose that particular path by which to apply Kirchhoff's voltage law is because the voltage VCCS is the only unknown voltage around that path, right? On the left-hand side, we have a known voltage of 60 volts. Across the middle bit on top, we have a known voltage of 15 volts. Across the right-hand side, we have that unknown quantity. And across the bottom, we have a voltage drop of 0 because those are all just wires or short circuits. And we know that the voltage drop across the short circuit is 0. So somebody help me out and tell me how to write a KVL expression following that path I've outlined in gold.
Dr. Hartman, I'm a little confused on what the sign conventions would be. I understand like what numbers would be there, but maybe like, I'm not sure.
Okay, no, that's perfectly reasonable. Questions are absolutely great. If you're having a question, I guarantee some of your peers are having the exact same questions. So the sign convention is simply which polarity terminal do we see first tells us what sign to give things. So for example, if we're starting from the bottom left-hand corner and we're going clockwise around this path, we see the negative polarity terminal of the 60 volt source first. So we'll start with negative 60 volts. Next, we see the positive polarity terminal of the 15 volt source. So we would have plus 15 volts. Then we see the negative polarity terminal of our voltage drop across our 5 ohm resistor. So we have negative VCCS and set this equal to 0. And then a little bit of algebra gives us 60 volts minus 15 volts, which is 45 volts. Does that make sense?
Yes, sir. Just like mathematically, could we also go the opposite way and it work out?
We absolutely could. So just for the sake of argument, let's go counterclockwise, okay? So the first thing that we would see, I'm going to do this over here on the right, and I'll do it in a different color so that it's obvious it's a separate equation. So if we went counterclockwise, the first thing we would see would be the positive polarity terminal of VCCS. Then we would see the negative polarity terminal of the 15 volt source. And then we would see the positive polarity terminal of the 60 volt source and set this equal to 0. It's literally the exact same expression that we just got, except multiplied by a factor of -1 because we're going in the opposite direction. When we apply our algebra, we would have VCCS is equal to, oh, I'm sorry, I made a dumb algebraic mistake here. Can't believe I'm making these simple mistakes, so I apologize. So let's pop back over here and let's see what I did wrong, okay? The KVL loop is absolutely correct, but the algebra has an error, okay? What I mean by that is I have a positive sign on the VCCS, and I also have a positive sign on the 60 volt source, and that's impossible because I've only moved one of them over to the other side of the equal sign, okay? So let's fix that real quick so that we'll get the same result either way. And I apologize for the mistake. So if we move VCCS to its own side of the equal sign, we should be left with negative 60 volts plus 15 volts on the other side of the equal sign, which should look like negative 45 volts. Now circling back around to what we were just doing, when we move the 60 volts over, that's going to, or excuse me, when we move the 15 volts over, that's going to look like positive 15. When we move the 60 over to the other side, it's going to look like minus 60, and we still get negative 45 volts. So if my ability to do simple algebra were better, we would have observed this a little faster. I apologize for my mistake, but we do get the same exact answer when we're not goofballs and make simple algebraic mistakes. So apologize for any confusion that my mistake may have caused. All right, so now that we know this voltage VCCS, we can determine our power supplied by our voltage controlled current source. Right? So VCCS is the current flowing through the voltage controlled voltage source, which is 15 amps. And the voltage drop over the current controlled voltage source, we get to be negative 45 volts. And just to be clear here, we have defined this voltage in such a way that the current is flowing into the negative polarity terminal, so that we simply have to multiply 15 amps times the value that we solve for to get the supplied power. 15 times 45 comes out to be 675 watts, and we should have a negative sign right there. So that's the power supplied by our voltage controlled voltage source. All right, so now let's figure out let's see. Let's figure out that current I 5 ohms. Does anybody have any suggestions on how we might go about solving for that current I 5 ohms?
Would you take the voltage you just solved for the negative 45 and use Ohm's law to solve for the current through that resistor?
That's absolutely correct. So our current of I 5 ohms is going to be that voltage drop VCCS divided by 5 ohms. But we do need to take into account that our current of I 5 ohms is flowing into the negative polarity terminal, which means we need to add a negative sign to our Kirchhoff, or excuse me, to our Ohm's law equation. So if we substitute in here, we're going to have negative 45 volts divided by 5 ohms gives us positive 9 amps. All right. So what I'm going to do right now, just to clean a couple of things up, is to add some more known information to our diagram. Okay. So we know that this current is 9 amps. We know that this voltage is negative 45 volts. And just for the sake of argument, I'm going to put it over here as well. So we only have two unknown quantities left to solve for. Let's solve for the current I-60 volts first, because we had a suggestion way back when that effectively told us how to do that. And I told you that we needed to know the current through the 5 ohm resistor first, and we just figured it out, okay? So I'm going to use KCl formulation number 1 on the bottom node here, okay? So KCl, I'm going to call it number 1 on the bottom node. My current flowing in is going to be 3 amps plus 15 amps plus 9 amps. My current flowing out is just I-60 volts.
Dr. Hartman, I have a question.
Yes, ma'am.
So I understand it was given to us, was it the 3 amps? If you don't mind scrolling up a little bit. Yeah, we solved for 3 amps and 15 amps and 9 amps. I'm curious about the sign conventions for all 3 of them, since 2 of them enter in the negative polarity and 1 enters through the positive.
Okay, so let's look at things real quick. So this was how IY was originally defined. I believe that's correct. If it's mistaken, somebody please tell me. But I believe that's how IY was originally defined. And we determined IY right here. Okay. Our current IY was flowing into the positive polarity terminal of our voltage Vx, which is why we have positive signs in this equation. We got 15 amps, positive 15 amps right here, not from applying Ohm's law or anything like that. This current was a dependent current, which was defined to be simply 1/4 times Vx. So since Vx was a positive number, the current is a positive quantity, okay? For this 9 amps here, we did that right here. When the current was flowing into the negative polarity terminal, we have to add these negative signs to our Ohm's law equation. And that's how we wound up getting this 9 amps. So we are being consistent in what we're doing. Anytime the current is flowing into the positive polarity terminal and we're applying Ohm's law, V is equal to I times R. Anytime the current is flowing into the negative polarity terminal, V is equal to negative I times R.
So it's not just how it looks on the circuit, it's about what you get mathematically.
No, it's absolutely about how it looks on the circuit, actually. I mean, the math is the math. It's how it looks on the circuit is what tells you whether or not you need to include the negative sign or not. Okay, so if we're looking here, we defined our current I5 ohms in this particular direction. So the current is flowing into the negative polarity terminal, which is why we get these negative signs. If we look at IY, the current is flowing into the positive polarity terminal, which is why we don't have a negative sign out front. So it's absolutely about what polarity terminal the current sees tells us whether or not we need to include that minus sign. And then we just let the math be the math. Did that clarify things?
Yes, sir. Yeah, I saw how I was thinking before and it was just incorrect. Thank you.
Oh, no problem. This passive sign convention stuff, it can be quite confusing, okay? So asking questions is a wonderful thing. I am absolutely happy to answer them, okay? It's gotta click or you're not gonna do very well in the class. So I'm always happy to answer these types of questions because I would much rather you have a problem with it and ask for some sort of explanation to gain better understanding than just suffer through it in silence and then give up on things. So ask any and every question you can think of. All right, so let's jump back around over here. We wrote a Kirchhoff's current law expression using formulation number 1, which states the currents flowing into a node have to equal the current flowing out of the node. And we applied it at the bottom node. And we observed that there is 3 amps flowing into the green node through the 20 ohm resistor, 15 amps flowing into the green node from the dependent current source, and 9 amps flowing into the green node from the 5 ohm resistor. And the only current flowing out of the green node is the current I60V on the left-hand side. So from here, we simply need to do a little bit of addition, right? So 15 plus 3 plus 9 looks like 27 to me. So 27 amps is equal to I 60 volts. From this, P 60 volts supplied is simply 60 volts times 27 amps comes out to be, I think, 1,620 watts. All right, so we have one last thing to figure out, right? We determined this guy, we have determined this guy. The last thing we need is the power supplied by our current controlled voltage source. Let's do what I've been doing, and whenever we figure out new information, let's add it. So the only unknown quantity we have left is this current ICCVS. We actually have 2 different ways that we can solve for it. Well, actually, I take that back. We have one way that we can solve for it, which is Kirchhoff's current law, but we have 2 different nodes that we could apply Kirchhoff's current law at in order to get the result. So what I mean by that specifically is we could apply Kirchhoff's current law at the red node, and we would find that that ICCVS is the only unknown quantity, or we could apply Kirchhoff's current law at the blue node. And again, ICCVS is the only unknown quantity. So pick a node, red or blue, and then tell me which Kirchhoff's current law formulation you'd like to apply.
Red, please.
Okay, red node. And do you want to do formulation number 1, number 2, or number 3?
I'm unsure as to which one would be the, I guess, the fastest way, or like the way that makes sense the most.
They're all relatively equally as fast, and they're all effectively identical. It's literally just a relative thing. So
Then 2, please.
number 2, okay, sounds great. We haven't done number 2 yet, so that's what we're gonna do. Okay, so formulation number 2 at the red node. So formulation number 2 is the one where all of the currents that are entering a node must equal to 0. So what color haven't I used yet? Let's do this. This blue, okay? So this current is entering the red node. This current is entering the red node. And this current is entering the red node, okay? So I'm going to tuck this in up here at the top so that we can actually see what's happening. So the current flowing up through the 60-volt source is 27 amps. The current flowing up through the 20 ohm resistor is -3 amps. And the current flowing from right to left through the dependent voltage source is ICCVS. So we'll set these equal to 0. And then solving for ICCVS, we get -27 amps plus 3 amps. Looks like -24 amps to me. So that is red number 2. Okay. Is it obvious where the signs on those different contributions came from, or would you like an explanation for that?
Oh, yes, sir. It makes sense. In my head, I did like which polarity terminal they went through. So I just did -27 amps minus -3 amps equals negative ICCVS. And I think it came out to the same thing.
So for these KCl expressions here in particular, where I'm not using Ohm's law or anything like that, I'm literally just comparing the direction of the current that I have solved for to the direction of the current that I quote unquote want based on the formulation of KCl that I'm applying, right? So for KCl version number 2, where we are saying all of the currents that are entering the node equal 0, I just drew all of these light blue arrows as if they were entering, and then I compared the currents flowing through those branches to the direction that's indicated by the arrow. So the 27 amps is in the same direction, right? This guy right here is in the same direction as this guy, so it got a positive sign. This guy right here is in the opposite direction as this guy, so it got a negative sign. This guy right here is in the same direction as this guy, so it got a positive sign. And that's how I wrote my Kcl equation.
I just did a face palm knowing how much easier it is to look at it like that.
It is what it is. As you get more and more practice, I sincerely hope that things will get easier. So that's my far too many years of experience do this has led me to that simple way of looking at things. Are the directions the same? Yes, positive sign. Are they different? Okay, negative sign. So from here, we can simply plug in our expression and solve for our power, right? So our voltage drop is 15 volts. So P CCVS supplied is 15 volts times -24 amps. And Here's a calculator. 15 is 360 watts. All right, so we have now solved for this guy too. Okay, so if I'm being very honest, this was a rather difficult problem in as much as the amount of analysis that we kind of had to throw at this guy was quite a lot. I would argue that this problem is a bit harder than anything that I will ask you to do, or hopefully anything that you will see on your web work, homework assignments, until we develop techniques which are called nodal analysis and mesh analysis. So if the analysis that we did here, and please forgive me for my multiple algebraic mistakes that I made, but if the analysis that we did here made sense to you, you are in wonderful shape for what we're going to be covering over the next several class meetings. If it seemed a little difficult, the best thing that you can do is to start working on those homework problems and those in-class assignments and things like that, and try to figure out effectively what it is you don't know, and then ask questions about it, okay? Literally no one yet has utilized my virtual office hours, which is perfectly okay. Today we are the class meeting because I chose to work a very difficult example problem, typically speaking. So our next lecture will be on resistor combination techniques, which I would guess most of you are at least moderately familiar with. I feel like I'll wrap that up within an hour pretty easily. So for people that want to hang out after I wrap up the lecture on Thursday to ask questions, by all means do so. Utilize the entirety of the class period to ask questions. I'm happy to help. All right, that being said, does anybody have any questions before we wrap things up for today? All right, well, there's still technically 12 minutes left in class, so I'm going to mute myself and, stop talking. If a question comes to you, I'll be here for another, 10 to 15 minutes or so. If not, have a great rest of your afternoon, and I will see you on Thursday.
Hey, Dr. Hartman.
Yes, sir.
I saw in the chat that people were saying here, did you check roll? Because I was like 2 or 3 minutes late to the Zoom.
Yeah, so I take roll by literally just having everybody type the word here into the chat. So type the word here into the chat.
Okay. I was just wondering because I saw that and I freaked out. I was like, he's not going to know that I was here. All right. Thank you.
No problem.
Dr. Hartman, I have kind of just a basis question.
Sure, what's up?
For the in-class problem on number 2, I was just wondering how you would approach a problem like this, because it's not it just looks a little bit different than the circuits that we had worked in class, and I want to make sure that my process stays consistent.
Sure. Okay, so for this problem here, okay, this is the one that you're talking about, right?
Yes, sir.
Okay, so for this particular problem, I ask you explicitly to use Kirchhoff's voltage law. So what my intent here is for you to identify Kirchhoff's voltage law paths that you can do where the voltage that you're trying to figure out is the only unknown voltage. So for example,
Oh, okay. Like, I get a little confused with voltage drops, like, because I don't even know what I'm trying to say. Voltage drops get me confused because it's not a part of a node per se.
right, yeah, so we're just taking the difference between different nodes and then going around in a loop until we wind up at the node we started from, right? So the path that I've outlined in orange here is a path that you could take to solve for the voltage Vx, because it's the only unknown voltage drop around this particular path.
So we don't necessarily have to take a nodal path. We can just take a viable path.
Right, so any path that starts and ends at the same node is valid.
Okay.
I just chose this one because it's the smallest one, which means I get to be lazy and do the least amount of math.
Okay. Okay. Thank you so much. That actually cleared a lot.
Oh, yeah, no problem. Yeah, this bit right here, the voltage drop across this middle thing is what stumps a whole lot of students. So I absolutely get it. I'm going to be a jerk and do stuff like that all the time.
Okay. Thank you so much, Dr. Hartman.
No problem.